Okay, so welcome everyone to our first session. We'll start with an introductory lecture by Jonathan Katz. Jonathan Katz is currently a senior staff research scientist at Google while on leave from the University of Maryland, where he is a professor in the Department of Computer Science. He is a co-author of the widely used textbook, Introduction to Modern Cryptography, now in its third edition. Katz has received numerous awards, including an Alexander von Humboldt Research Award, a UMD Distinguished Scholar Teacher Award, and an ACM SIGSAC Outstanding Contribution Award. He is a fellow of the IACR and the ACM. Please welcome Jonathan.
Thank you so much for the introduction. And actually, I want to thank Alex, and I want to thank the entire organizing committee, Liz, Sharon, Akira, and Marco. They mentioned that they started working on the idea for this workshop 2 years ago, and they've really been heavily involved and working hard on it, not for the entire 2-year period, but especially over the past couple of months. We had multiple meetings and emails going back and forth, and they really put in a lot of time and effort, and they put together a great program. And so please join me in thanking them for all their work. I wanted to just say before I begin that this lecture, in particular the first lecture, is going to be really introductory. I didn't really know exactly what background people had coming into this lecture. Actually, and I don't know if I'm standing in the right spot here. Am I good? Okay. So I didn't really know what kind of background people had, and I'm sure that there are people who have seen this material before, and I'm sure that there are many of you who have not seen this material before. And one of the great things about the internet is that now you can find all kinds of videos online where you can learn about zero-knowledge proofs. Maybe it's not so great if you're the speaker because this is going online. But anyway, so you have them online. But one of the bad things about the internet is that everything's available online. So what do you need to watch this here for? What's the advantage of being here? And the real advantage of being here is to have the opportunity for interaction. And so I would really encourage you to ask questions during the lecture. I don't get paid any less if I don't finish the slides. It's not possible to get paid less. But okay, so I don't feel any need to finish everything. We can go a little bit into the coffee break. I can make up some of the material later or whatever. So really, take the opportunity to ask questions, and I'm happy to take them at any time during the lecture. And that goes for people in the overflow room and the people online as well. So I'm really happy actually to be giving a talk like this, and that there's a workshop like this taking place in a Center for Mathematical Sciences. And it gives me an opportunity, first of all, to say what excites me the most about zero knowledge. And I think what excites me the most, really, every time I look back at the material, is the applications are great, and the applications are wonderful, and the applications are what provided the funding for this workshop. But really what excites me is the underlying mathematics. And it's unbelievable to me, and I think it would be unbelievable and surprising perhaps to a lot of mathematicians in this building, that to see that algebra, right, what does algebra have to do with computer science? Algebra, basic things that you learn about groups and fields and polynomial arithmetic and things like that, have incredible applications with computer science. And the interplay between the two is, I think, what's really most exciting and surprising and interesting about this. And the other thing that I think makes it relevant to give a talk like this in a Center for Mathematical Sciences is that part of what this work did, and this is going back now to the 1980s, is really give a new perspective on what it means to give proofs, right? Mathematicians have an idea of what a proof means. The idea of a proof goes back thousands of years. It was axiomatized in the early part of the 1900s. And if you think classically about what a proof is, right? If you're trying to prove some theorem, some statement, call it X, right? When we think about what this means in the context of mathematics, we typically, or I think mathematicians always think about it as a static object, right? You write down the proof and then it sits there in the journal or on the blackboard. And anybody else can come along and verify that proof line by line using some deterministic procedure, right? And you can axiomatize this, like I said, and you can specify what exactly the rules of the game, so to speak, are, what are valid transitions in a proof. And once you specify those, then it really becomes completely deterministic and an algorithm and something that's possible of being algorithmatized. I don't know if that's the right word. But anyway, you can go through and check it in some specified fashion. And of course, if the statement is false, then there, by definition, really, then there is no proof that will verify correctly for this false statement X. And so you can think about this. This is really a computer science viewpoint, but the way that I think about this is that you have your prover on the left and your verifier on the right. They have some statement X. The prover is trying to convince the verifier about the truth of that statement X. So they'll spend their time writing down this proof, right? Maybe in the journal, like I said, and they'll, they'll email the proof over to the verifier. The verifier can then take that proof pi, go off and apply this deterministic checking procedure to determine whether the proof is valid, in which case the theorem is proven. And this actually has a connection to the complexity class NP, in some sense, where we'll say that a language is in NP, and I think you've all seen this before, but feel free to ask if you haven't. But we say that a language is in NP if there's a deterministic verification procedure or verifier algorithm that I'll call here VL, because the verifier will depend on the language, running in polynomial time. So this is something that has no counterpart in the mathematical world, but in computer science, we're interested in the ability to complete the checking of the proof in some reasonable amount of time, such that the following holds. If X is in the language, think about that as meaning that the statement is true, then there exists a proof pi that somebody can write down, somebody can come up with, that will convince the verifier. So there is a proof pi such that when you run the verification procedure on the given input and that proof pi, it will output 1. And this is an if and only if relationship. So what that means is that you have two properties. You have a completeness property, which says that if X is in the language, then there does indeed exist a proof that you can give the verifier that will cause the verifier to accept. And if X is not in the language, then there is no proof that will make the verifier accept, or flipping it around, for any proof pi star that you provide to the verifier will output 0. Okay, so that corresponds really to the picture or the description we had on the previous slide about what it means to prove statements mathematically. And computer scientists beginning in the 1980s began to wonder, why do we need to limit ourselves to this notion of what it means to prove a statement? We can actually allow ourselves to be a lot more general. Okay, so again, the traditional view here on the left views the proof as a static object with a deterministic verification procedure, such that false statements do not have proofs that verify. But we can relax that, or maybe generalize it, and think about a much more expansive notion of what it means to prove something. We can allow for an interactive process between a prover and a verifier, right? The prover and the verifier can interact and thereby allow the prover to convince the verifier that something is true. We can also allow the verifier to potentially use randomness in order to check what the prover is telling it, right? The prover may be trying to cheat and give a proof of a false statement, and the verifier can use randomness in some way in order to catch that and make sure that it only accepts proofs of correct statements. And in fact, I'm not really going to discuss this in detail, but you really need both of those, the interactivity and the randomization, in order to get any really meaningful generalization of what we have on the left-hand side. Now, a drawback of that is that once you allow randomization, you realize that again, you don't really get anything interesting unless you also admit for the possibility that the verifier might occasionally accept a proof of a false statement. Okay, and this is maybe something that bothers mathematicians and maybe why they didn't go this route. But from a cryptographic viewpoint, if we can set that probability low enough, then it's really inconsequential and we can effectively ignore it. So it is possible that the verifier will accept a proof of a false statement, but this can happen, or we'll make it happen. We'll set the protocol up so that it happens only with very small probability, and we can make that probability as small as we like. So the picture you can have in your mind now is similar to before. We have the prover on the left and the verifier on the right. They have the statement X that they're interested, or that the prover is interested in convincing the verifier is true. But now we'll allow for multiple rounds of interaction between the prover and the verifier, at the end of which the verifier will output a determination of whether to accept or reject. And accept means that it accepts the proof and that it believes that, therefore, that the statement is correct. Reject means that it does not. So we can formalize this notion, and we can formalize kind of similar to the way we formalized the static notion of a proof as the complexity class NP. We can define a complexity class around these interactive protocols and say that a proof system for a language L is going to now be a pair of algorithms, okay, a prover algorithm and a verifier algorithm, where the verifier algorithm runs in probabilistic polynomial time. So we're still interested here in maintaining an efficient verifier. In this definition, we're not going to care about the complexity of the prover. right? And that's because in the analogous case of NP, we didn't care about the complexity of generating the proof pi. We only cared about the complexity of verifying it. So here too, we're going to keep the complexity of the verifier polynomial, but the prover, could potentially be unbounded. And we're going to require the same completeness and soundness properties as before, but now they're going to be defined with respect to the interactive protocol here. So if X is in L, if X is in the language, then we're going to also add in a security parameter here. This is actually sort of a little bit of a non-standard definition, but I think it's a useful one, especially in the context of cryptography, where it's natural to introduce a security parameter. If X is in L, then for all security parameters, when we run the prover and verifier, this bracket notation here just means an interactive protocol is being run between the prover and verifier. We're looking at the output of the verifier, and the common inputs to the parties are what's in parentheses here. So they both have input the security parameter and the statement, and we're just requiring here that the prover can convince the verifier with probability 1. The soundness property here is going to be that if X is not in the language, then for all possible interactive algorithms, P star, not necessarily the intended one, and for all security parameters lambda, if we run the protocol between the possibly cheating prover and the honest verifier on a false statement X, then the probability with which the prover is going to be able to convince the verifier to output 1 to accept the statement as true is going to be bounded by 2 to the minus lambda. Okay, and as we were saying earlier, you can make lambda as large as you like, drive that probability down as much as you like to make the probability of accepting a false proof as low as something you're comfortable with. Good, and you can also, I'll just mention, you can relax the completeness to be 1 minus negligible, but in practice, most of the examples we have naturally have perfect completeness, so you don't lose much by requiring that. And we're going to let IP be the complexity class of languages L that have a proof system satisfying these properties. So clearly, IP at least contains NP, because NP is kind of a degenerate notion here where the interaction is just a single round. Well, we'd like to know, obviously, how much larger IP is. And one other note I want to make, just to introduce the terminology, although it won't really come up in this lecture here, but it'll come up in some of the later lectures, is that we can also imagine relaxing the soundness property a little bit. And again, this is something that really makes sense in the context of cryptography more than in the context of complexity theory, where if we restrict the soundness property to only hold for cheating provers that run in polynomial time, then we get what's called an argument system. So we have the notion of proofs where soundness holds against all provers, and arguments where soundness only holds against polynomial time provers. Question?
So I have a question. It's both a genuine question and also like modeling asking of questions. Yeah.
Good.
So my question is, why is that not the standard definition? Seems very nice.
The lambda, you mean?
Yeah.
Oh, I think just because in the context of complexity theory, well, let's see. So there are a couple things. So in the context of complexity theory, there's not usually a security parameter, and so it wouldn't come up. And the other thing you can do, which I actually don't like, but what you can do is you can effectively take the length of the statement as a security parameter. The reason I don't like it is because you might be interested in a particularly short statement, but yet you still want the large soundness, or the good soundness, rather. Maybe in the context of cryptography, this is standard. I don't know. But I think in complexity theory, you wouldn't find the lambda.
So, sorry, just to follow up on the last statement you said, or by very short input, you mean like logarithmic or process size?
Well, I mean, I just mean that you care about this input, and this input has 25 bits in it. But I want soundness 2 to the minus 100. So I should be able to kind of independently set the length of the statement and the security parameter that I want. Actually, you can flip it around as well, right? I might have a 1,000-bit statement, but I don't need a 1,000-bit security parameter. That would be overkill. And so maybe I get better efficiency by limiting to an 80-bit security parameter, even though my statement is 1,000 bits long.
In complexity theory, I think it's like most of like the input is the main part. It's kind of the input of the X is kind of proportional to the 1 to the lambda. So that's why I'm asking. I guess like
right. Oh, I see what you're saying. Well, but in complexity theory, it's a little different because in complexity theory, I mean, actually, so in complexity theory, I think the way you would define it would be to have the soundness be 1/2 for regardless of the length and regardless of any lambda. And then if you wanted to, you could always amplify, but they would define it that way. But I think the main point is that in complexity theory, there's no notion of a security parameter.
Yeah, just a question. Can you please repeat the meaning of the notation of 1 to the lambda?
Oh yeah, one, right. So yeah, this is a great question. So yeah, 1 to the lambda is 1, right? So I could have simplified. Yeah, I get this question, you wouldn't believe actually, but it's a good question because it's really crazy notation. But 1 to the lambda, what it means is just a string of lambda ones, and the only purpose for it is to allow the party's running time linear in lambda, not linear, dependent on lambda. I'm glad that somebody asked that.
We implicitly parameterize L, the language, by lambda as well.
No. So lambda has nothing to do with L. For any L, you can always choose your lambda to be whatever you want. I mean, this is how things work in practice, right? In practice, you have some language, and then you implement your protocol, whatever. But then you can choose what you want, what you feel comfortable with for the soundness. And if you're comfortable with soundness 2 to the minus 40, then you can set lambda to be 40. If you want it to be 2 to the minus 128, you set it to be 128.
Does this mean that like our verifier should run in time linear and lambda and
Polynomial.
polynomial and lambda? So does this mean that if x is too long, the verifier cannot even read the entire input?
Yeah, that's a good question. Let me think 1 minute. I mean, I think I would say maybe it depends. Let me think a minute. So I had in mind actually that the running time of the verifier was polynomial in the sum of the lengths of the input and lambda, so that problem doesn't come up. So it always has time to read x in this case. Yes.
This was the reason for my first question, if L is parameterized by lambda as well, so that.
Well, it's not parameterized by lambda, right? It's just that the running time of the verifier is allowed to depend on lambda. At lambda and the length of x.
Okay, thanks.
Why does the soundness definition use P star and not P?
Oh, because right. So P represents the honest prover. P represents, if everybody's honest and we're just trying to run the system honestly, what should the prover do? But for soundness, we're concerned about what a cheating. I mean, we're explicitly concerned. I mean, an honest prover will just say, hey, the statement's false. Right, so we care about defending ourselves, if you like to think of it that way, against the behavior of a dishonest prover. I'll also just note that this is again more of a cryptography thing rather than a complexity thing. I said earlier that we don't care about the complexity of the prover, but in the real world and in cryptography, we generally do care about the complexity of the prover. And so I'll just mention here that we would like P to be efficient for languages in NP if it's given a witness or a proof. I think I said earlier this notion that you can call things proofs or witnesses. A question?
Yeah, I was just wondering about the languages L. So one language is the set of prover and verifier algorithms. Is that correct, or?
A language.
Definition of a language.
So the definition of, well, okay, a language is a set of strings, and we're saying that a language is an NP if there is a proof system for that language.
Oh, okay.
And then this is what it means to be a proof system.
Thanks.
Yeah.
When you say would like P to be efficient, is that a matter of definition or is that?
No, it's not in the definition. It's not in the definition. I mean, you can define things like that if you want, but it's not in this definition. Okay. Yeah, by the way, is there anybody online with any questions or in the other room? Anyway, you can let me know, I guess. It's a little dangerous that anybody can just unmute themselves and call out, but I'm glad that nobody's malicious out there. Okay, so what are some advantages actually that we can gain by generalizing the concept of proofs in this way? So there's a couple that I thought of, and maybe there are others that I'm missing here. So one advantage is that this might be applicable to languages beyond NP, right? If IP, the class of languages having interactive proofs, ended up being equivalent to NP, it probably wouldn't be too interesting, at least to complexity theorists. So we can hope to go beyond NP in this way. We can also hope to achieve stronger properties. So when we talk about zero knowledge, right, this is something where even if you're looking at languages in NP where we have non-interactive proofs, you may get something interesting by allowing for interaction because you can add additional security properties to that interaction. Okay, so we'll see that with zero knowledge. And you can also hope for more efficient verification than what the verifier can do alone. So this is interesting now, even for languages in P or BPP. So things that the verifier might even be able to decide the truth or falsity of a statement on its own, but maybe it takes, I don't know, n to the fourth time to do that. And perhaps by interacting with the prover, the verifier might be able to be convinced of the truth of the statement in linear time. Okay, so you can hope for that kind of advantage as well. And we're going to, in this talk, I'll focus on the second one. In my later talk, I'll focus on the first one. And I think, later in the week in other lectures, we'll focus on, well, I'll talk about the third one as well. But, the rest of the week is going to basically be about, I think, the third one largely. All right, so let's talk about zero knowledge. Let's talk about this extra property that we can have once we allow for interaction in our proofs. So the goal of a zero knowledge proof, roughly speaking, is to convince a verifier that some statement is true, right? Again, namely that some X is in a particular language, without revealing any information beyond that. Okay, somehow we want to convince the verifier that something is true, but not tell them anything else about why that statement is true. And if you think about it a little bit, right, it's not so clear how you would define something like that. Right? I mean, I hope the intuition is sort of clear, right? I feel sometimes that when you're sitting in a lecture and it's like that, the professor tells you this is true, they talk and they interact, and but at the end you have no idea why it's true, but you're willing to believe it's true for the purposes of the exam. But it's really, if you think about it, right, it's a little bit more than that. Here we're saying that the prover actually does not want the verifier to learn anything beyond why some statement is true. Okay, and maybe if you've never seen this notion before, it's even a little bit odd why you would ever want some property like that. And I'm not going to try to really motivate it other than by saying that you can imagine it would have applications to privacy, right? Where you want to prove to a verifier something, but you don't want to prove to them everything. Okay, and I hope some of the other speakers later in the week will touch on specific applications, but that's going to be the general idea. So how do we define this notion of a verifier not learning anything beyond the fact that the statement is true? So the way we're going to do that, and this is something that developed over the course of a sequence of papers in the 80s, is that we're going to look at the interaction between the honest prover and a verifier. And we're going to say that the proof, this interaction between the prover and the verifier, is zero knowledge if the verifier is able to simulate its entire interaction with the prover. So the idea being that you have some interactive protocol being run between a prover and a verifier. This interactive protocol is going to be sound. So if the prover is able to convince the verifier at the end of the interaction that the statement is true, then we have very high confidence that indeed the statement is true. Nevertheless, if you look at the entire transcript of the interaction between the prover and the verifier, the zero knowledge property says that the verifier has the ability to simulate that entire transcript on its own. And that tells us that the transcript did not leak anything to the verifier other than the fact that the statement was true, because the verifier would have been able to simulate that entire transcript on its own. Okay? It's a little bit of a counterintuitive idea, but we'll see when we give examples, you'll see exactly how it comes up in the mechanism.
It's not like the verifier would be able to convince other verifiers.
No, right. So the difference actually, and it's a very subtle one, is that the interaction is what's providing the soundness. But at the end of the interaction, you have a static transcript, right? It's just message 1, message 2, message 3. And the claim is that the verifier sort of simulated that entire transcript on its own, but it doesn't help it now go and convince somebody else, because if it now turns around, it has to now interact, in an online way with some other verifier, and it's not going to be able to convince. I mean, well, for a zero knowledge proof, it will not be able to convince another verifier because it didn't learn anything. But yeah, so exactly right. The interaction is what's giving you the power here. The simulation is giving you the fixed transcript that you got, or the distribution on transcripts at the end of the interaction.
Is that because the randomization originated from that specific verifier?
Well, the randomization is a big part of it, right? So yeah. So I mean, actually, you can give kind of a trivial example, and trivial in the sense that it's not interesting, but it illustrates the point. So let me think. What's a trivial example? Well, if you know commitments, I guess it's a trivial example. So you can have some crazy protocol where the prover commits to a value, the verifier sends a random value R, and the prover is supposed to open the commitment to R. Okay. And I don't know, well, okay, I can start giving concrete examples, but, so the point is, so that's going to be something where in general, it's going to be hard for the prover to convince a verifier. Okay, so I have to make the example more complicated, I guess. Do you get the idea, or should I make the example more complicated?
I get the idea.
Okay, good, thank you. Maybe I can think of a better example, but yeah. Oh, yeah.
It's possible that you're going to address this later on, but I was wondering, what is it with the interaction with the verifier, with the prover, sorry, that indicates that we did have that actual interact? What is it about the transcript that indicates that we actually had that?
Oh, nothing, actually, nothing. So this is something related to deniability, where the prover could potentially, later even deny that they ever ran the protocol, right? So the verifier is convinced that the statement is true. The verifier is even convinced that the prover knows why the statement is true. But yet, even if the verifier turns around and tries to convince somebody else, hey, the prover ran the protocol with me, it doesn't work because the verifier could have simulated that interaction on its own.
So the value of the transcript is not so much an attestation as it is for the verifier itself to be convinced.
Yeah, actually, in some sense, the transcript has no value. After you're done running the protocol, you can throw it away. It has really no value. Yeah, so this is actually very, these are good questions because you can think about them later in the context of non-interactive zero knowledge, where some of these statements are not quite true, or not true. But at least for interactive protocols, it's exactly right that the transcript you get means nothing, and the whole point of the interaction is the interaction itself. Good. So let's see how we can formalize that. So before I do that, I have to introduce a notion of computational indistinguishability. I kind of did a little bit like fast and loose here, but let's see if I don't get into trouble. Maybe Markov will call me. But let's see. So I just want to introduce some terminology here. So if we let think of X and X prime as algorithms. And what they're going to do is they're going to take some security parameter and some input, and then once you fix some input to these algorithms, they define some probability distribution. Okay, so they're randomized algorithms. So there's some random tape that's not in the notation here, and so for some fixed input, x and x prime each specify some distribution. I haven't really said much yet. So we'll say that they're computationally indistinguishable if for all distinguishers D running in time polynomial in the security parameter, and all lambda and x, and all lambda and x in some set S. So I want also to consider, I may be restricting the class of inputs here that I'm interested in to some set S, and all auxiliary inputs Z. The probability that D, when run on this set of inputs here, outputs 1, right? Where these are things chosen from the distribution specified by algorithm X. Oh, I missed a prime here. And minus the probability where D is given something output by X prime should be negligible. So actually, I don't want you to like stare at this definition. It's kind of here just for like completeness. If it's wrong or whatever, or if you don't understand everything, it's not really super important. What I did want to stress, though, is that D, in addition to being given the output of either X or X prime, it's also given X itself. Right? So in the context of zero knowledge in particular, D will be given not only the statement, but also the witness that the prover might be using. That's all I wanted to get across by this definition. And just some notation is that I'll use this notation here to indicate that they're computationally indistinguishable. Okay, so I mean, have people seen computational indistinguishability before? So, okay, yeah, if you haven't, I mean, it just means that, an efficient distinguisher can't tell two distributions apart, and you can just forget about the math here. All right, so let's let PV be a proof for an argument system for some language L with relation R. We'll define the notion of first honest verifier zero knowledge. We'll say that this PV is honest verifier zero knowledge if there is a probabilistic polynomial time simulator S such that the following holds. Okay, we're going to look here on the left-hand side at the distribution of the output of the verifier. And this output here should be the entire transcript of its interaction with P, not just the final bit that it outputs. We're looking here at the output of the verifier after an interaction with the prover. So actually, you could just think of this as really being the set of all messages sent by the prover to the verifier, plus the internal state of the verifier throughout that interaction, which essentially is going to be just its random tape. We're going to look at that distribution. The range of interest here is going to be pairs of statements X and the associated witness W, right, in the given relation R. Okay, so we're looking at the distribution of the transcript when the honest prover interacts with the honest verifier. And we're going to say that the simulator is able to run given access only to the instance X, and it's going to be able to produce an output that's computationally indistinguishable from this transcript. Okay, so again, at the high level, we have on the left-hand side the distribution of transcripts generated by an interaction of the honest prover with the honest verifier on a particular input and witness pair. And we're saying that the simulator is able to simulate those interactions. The simulator is given only X and not the witness, is able to generate a transcript which is computationally indistinguishable from the transcript of the real interaction between the prover and the verifier. Right, so again, this just means, this is just formalizing the idea that S can simulate the transcript of the interaction of the prover with the honest verifier. And crucially, right, the simulator is doing this without access to the witness, right? If the simulator had the witness, it could just run P itself and run V itself and actually, well, emulate them both and thereby, give a good simulation. The hard part here is that we're requiring the simulator to do this without access to the witness and only with knowledge of the statement itself.
So you asked to be challenged. Can you go?
Oh, I was asking not to be challenged.
No, I'm not joking. You might also give us a chance to think. Can you go one slide back? I was just wondering how you find it.
Yeah.
Yeah, you defined it for all X in S.
Yeah.
Yeah, I was wondering whether you could also say, you could define it for a fixed S and then say for all, for a fixed X and say for all X, it needs to be indistinguishable.
Are you asking about why I restricted to things in the relation?
No, that's fine. But why you kind of defined indistinguishability of families rather than just distributions for a fixed X? And then you could say for all X.
Oh, I see. Well, that would give you, I think, an instance-dependent simulator, right? Every instance would have its own simulator.
Yeah, I see.
Yeah, I suppose you could. I don't think I've ever seen that before, and I'm not aware that it gives you any power. I think the challenge. Let's see how I define it here.
You could still fix the simulator first, right? There is a PPT simulator S, a fixed S, such that for all XW.
Oh, but that's what this
in the
gives you.
relation-
That's what this gives you, right? This already gives you that.
Yeah, I think so. But I would have moved the XW in the relation up to that for all XW in the relation.
Yeah.
You just have.
Oh, I see what you're
Just
saying.
an
Yeah, you probably could. I think it's equivalent.
Yeah.
It's just a presentation issue. Yeah.
Just to check the relation with the previous definition. So basically, this distinguisher should get the witness, but still they cannot tell them.
Yeah. Right. That's actually critical. Because or let me say it even better, like even if the distinguisher has the witness, it still can't distinguish.
Right.
And the reason why I say it's critical is because you can have many applications actually where there's more than one witness, and maybe even in the real world, somebody knows one and doesn't know the other, and you don't want, even in that case, that party to be able to tell which witness the prover used, and so this will give you that.
Actually, why are you interested in honest verifier zero knowledge? Whereas
I'm actually not that interested in it. I mean, I just put it here, but the next slide will be malicious. But yeah, I just put it here that for completeness. Good. So here we are. So yeah, so we can also define more general zero knowledge, and this is really, I think, getting at the point that why are we interested in an honest verifier when we really have to be concerned about the potential for a malicious verifier? And so this gives you that, and it's the same as the previous definition, but the difference here is that we say now that for every polynomial time possibly cheating verifier, V star, right? So not the known verifier, but some completely arbitrary verifier, there should be a simulator that can simulate the interaction of that verifier with the prover. And the only thing that's kind of obvious when you think about it for a minute, but worth pointing out, is that the simulator has to depend on the verifier, right? If the verifier always sends zeros, then the simulator had better simulate an interaction of what the prover does when it only receives zeros. And if the verifier, behaves honestly, then the simulator has to, simulate an honest execution. So the simulator really has to depend on the verifier. But what we're requiring is that no matter what verifier you give me, I can find a simulator that can simulate the interaction of that verifier with the prover. Good. And if you've seen, anyone care about black box zero knowledge? If not, nobody cares, and I don't have to mention it. Fine. Good. Good. So I want to introduce another property. So now you have zero knowledge in your head. I want to introduce another property called proofs of knowledge, also sometimes called knowledge soundness. And this is actually, you can think of as protecting against a cheating prover. So the notion of zero knowledge is ensuring some security property for the prover, for the honest prover against a cheating verifier. The notion of a proof of knowledge is protecting the honest verifier against a possibly cheating prover. And it's basically a stronger notion of soundness. Essentially, what the intuition says is that if you have a prover, potentially malicious prover, who can successfully convince the honest verifier, right, make the verifier accept with high probability, then the prover must know a witness. Okay? Not only that there exists a witness, which we know anyway from the soundness of the protocol, but the prover has to know a witness. Okay? What does it mean to know a witness? We'll have to define in the next slide. But let me just say why this notion is even interesting to think about. Where did somebody come up with this idea? Well, I think really the reason people came up with the idea, well, I don't know which was the actual reason, but it's interesting for at least two reasons. So first of all, you can have interesting protocols, interesting interactive proofs, even for so-called trivial languages, right? And one example, like kind of the classic example of a quote-unquote trivial language is this language here, where I have some finite cyclic group, and we have some generator G, and the language is going to be all elements Y for which there exists an X with Y equal to G to the X. So why is this a trivial language? Well, it's trivial as long as you can test membership in the group efficiently, because if I can test membership in the group efficiently, then yeah, I can just look at Y. If it's in the group, then it's equal to G to the X for some X because G is a generator. But this property of knowing a witness says something more, right? It says not only does there exist a witness, which is true for everything in the group, but the prover knows a witness. Right? So that's why this notion might be useful. The other place where it's useful, which I think we're not going to get to see because this is not a school about protocols, but when you're building larger protocols from these interactive proofs, starting with them as a building block, then it becomes very useful in the proof of security for the overall protocol to be able to leverage the fact that the prover actually knows a witness. And not only that, but we'll see on the next slide, we have the ability to actually extract that witness and then potentially use it for something later down in the protocol. So this becomes very useful when these proofs are not just looked at as in a standalone fashion, but when they're used as building blocks for larger protocols. And I just want to have a little aside. I don't know, I think I'm going to skip this aside because it's, oh, I didn't do the aside yet, so good. Okay, so it's coming up. I'll just skip it because for lack of time. So how do we define the notion of proof of knowledge? So let's let PV again be a proof or argument system for a language L and NP with some associated relation R. So we're going to say that this proof system or argument system is a proof of knowledge with respect to that relation if for every probabilistic polynomial time possibly cheating prover P star, there's going to be an expected polynomial time knowledge extractor E such that the following two properties hold. Okay, so what E is going to do is it's going to have two outputs actually. It's going to have two outputs where the first output you could think of as a transcript of the interaction between this prover and an honest verifier. And the second output is supposed to be a witness. So what we require is that if you run this knowledge extractor on the given input X, then it outputs a view and a witness W, such that the probability that that view represents an accepting transcript and XW is not in the relation is negligible. Which, if you flip it around, means that anytime E outputs an accepting transcript, almost always it should also, along with that, output a witness W, satisfying the relation for that particular statement X. Okay, so this is really why it's called an extractor, because it's in some sense extracting a witness W for the given statement X. Now, in some sense, right, this by itself is a little bit, well, it's either meaningless or too strong, because maybe E never outputs an accepting transcript, right? And then it's trivial to satisfy. But that's why we also have the second property here, which says that the the view, right, the first output of this knowledge extractor, the view that's output by the knowledge extractor, should be computationally indistinguishable from the interaction of the cheating prover with the honest verifier. Right? So it's kind of a lot to unpack, and I think just the way that you need to think about it in the context of this lecture is that, well, let's think about it this way. Let's say the prover P star manages to convince the verifier with some probability P. Doesn't have to be 1, right? It could be 1/10, but it convinces the verifier with some probability P, which is non-negligible. Then what that tells you is that E is going to output an accepting transcript with probability negligibly close to P, so negligibly close to 1/10. And then the first condition tells you that the probability that it outputs an accepting transcript but doesn't output a witness is negligible, which means that it's outputting a witness essentially with probability P as well. So, one way to think about it is that at least what this gives you is that if the cheating prover convinces the verifier with some probability P, then the knowledge extractor will output a witness with roughly the same probability.
Somehow this sounds like I would be able to extract, like looking at the transcript, I can somehow extract the witness, or
well, it's going to, well, okay, so it depends, right? If we're in NP and we're just having a one-round proof where the prover sends the witness, then it's trivial.
okay, that's clear. But I mean, okay.
But now what I want to ask you is, can you have a proof which is both zero knowledge and a proof of knowledge?
Okay, so this is without we're considering it in the.
Well, I'm just defining it right now, and we might have a proof of knowledge which is not zero knowledge, but what we really want is something which is both zero knowledge and a proof of knowledge.
This is exactly why I was asking. Like, it sounds like this cannot be zero knowledge, right? Because it's.
Well, I don't know. I have a slide on it later. I hope it is.
No, but
Yeah, this is actually really.
the transcript.
Yeah. These are in tension with each other, right? Right. On the one hand, so by the way, it doesn't say that the extractor gets a witness from the transcript, right? And really, what's going to happen is that it's good. You can imagine. Well, I don't want to give too much away, but you're not getting the witness from the transcript. You're doing more than that. But somehow, yeah, these properties of being both zero knowledge on the one hand and a proof of knowledge on the other, they're definitely in tension with each other. And so, yeah, we're going to have to work a little bit to get both.
So the extractor is interacting somehow also, or is it?
You could, yeah. So what's going to be the case is that the extractor, right? The extractor can depend on the prover, and so we can in particular have the extractor run the prover, and what we're going to do is run the prover multiple times. And the claim is that, okay, if it's zero knowledge, running it once doesn't give us anything, but maybe running it, a bunch of times, maybe we get something from that.
What's the difference between an extractor and a simulator?
Well, the technical difference so far was that the simulator was for the zero knowledge property, and this is for the proof of knowledge property. However, you can note that the extractor is also simulating. This extractor is simulating the interaction of P star with V, but just doing that is trivial here, because to do that, if all you cared about was simulating, all you do is run the honest verifier. So it's not really interesting. It's only interesting when they're coupled with each other.
This notion is often called the witness extended termination.
Yeah. I mean, it's equivalent. So, but yeah, this is a much clearer way than the original definition. Yeah, so proof of knowledge in particular implies soundness, right? So going back to the example before, I said that if the cheating prover can convince the verifier with some probability P, then the extractor can output a witness with probability roughly P. If there's no witness, then clearly P has to be negligible, which implies soundness. So I see now that we're running slightly late on time. I don't know. Well, let's just see how it goes. But I mean, should we go into the coffee break or not?
I think so, yeah.
Okay. Great. Wow. I like the conversation. It's like all right. People online are welcome to get coffee, I guess. Good. So let's look at some zero knowledge proofs for NP, zero knowledge proof of knowledge. So I have to introduce one building block before I can do that, and I'm just going to introduce it at a relatively informal level, and that is the notion of a commitment scheme. So a commitment scheme, let's talk about non-interactive commitments, is just an algorithm that takes as input an input X or message X and some randomness R. And the way you would use a commitment scheme is that in some initial phase, the sender will send a commitment to the verifier. And then in some later phase, the sender can open up the commitment, as it were, by just revealing X and R. So COM is going to be an efficient algorithm. So what the verifier can do in that case is it can just rerun com on X and R and check whether it's equal to what the sender sent it in the first in the first phase. Okay? And the properties we want here are binding and hiding. The binding property says that even a cheating sender cannot generate a commitment C that it sends over to the verifier in the first phase, with the property that it can later successfully open that commitment to two different values, X and X prime. So it shouldn't be possible for the sender to find a value C along with values XR, X prime, R prime, such that X and X prime are different, but com on XR equals C equals com of X prime, R prime. And the hiding property says that the receiver should not be able to learn anything about X from the commitment alone. So basically, until the sender reveals X in the second phase, the receiver doesn't know anything about X. And you can define either property both in a computational sense or a perfect statistical sense. It's not going to matter too much for the stuff we're talking about here today, but it is interesting to think about getting commitment schemes with different sets of those properties. And what we're going to do is show a zero-knowledge proof of knowledge for the NP-complete Hamiltonian cycle problem. And this is going to imply a zero-knowledge proof of knowledge for any language in NP. There's a little bit of work actually you need to do in order to prove that formally. You need to show not only the fact that you can reduce any language in NP to the Hamiltonian cycle problem, but that it sort of allows you to go to map the witness as well in both directions. But you know, I can leave that as an exercise for people to think about. But essentially, it's going to imply a zero-knowledge proof of knowledge for any language in NP. Once we can handle an NP-complete problem, it's going to essentially imply that we get zero knowledge for anything in NP. So just to remind you about what the Hamiltonian cycle problem is, here we have a directed graph. I have no idea why the resolution is so bad. I'm surprised. Anyway, it's a directed graph. And a Hamiltonian cycle in the graph, if you can see that, is basically a cycle that passes through every vertex and comes back to the starting point. So in this particular graph, you have a cycle. You follow the edges around, and the directed edges, and you get back to the starting point. And this is known to be an NP-complete problem. Namely, if I give you some large directed graph and ask you, is there a Hamiltonian cycle in the graph, that's an NP-complete problem. So how is this going to work? Well, the initial inputs to the prover and the verifier are going to be some directed graph G that they agree on. And the prover will also know a Hamiltonian cycle in the graph. So that's going to be the witness, right? We assume we want the prover to be efficient if it knows a witness. So the prover is going to be assumed to know a cycle in the graph. And it's trying to convince the verifier that the graph G does indeed possess a Hamiltonian cycle. So we're going to have a 3-round subroutine in which the prover and verifier do the following. So first, the prover is going to pick a uniform permutation pi. This is a permutation on the vertices of the graph. So it's basically thinking, you know, the labels on the vertices of the graph. And it's going to commit entry-wise to the adjacency matrix of the permuted copy of G. Okay, so you take your graph G, the prover and verifier agree on the graph. They agree also on the labeling of the vertices, right? They agree on some adjacency matrix of the graph, which, you know, is equivalent to defining the labeling of the vertices. The prover is now reshuffling all the labels on all the vertices and mapping, of course, the corresponding edges, right? So if there's an edge in the initial graph between two vertices, then that same edge appears, the directed edge, between the permuted vertices in the second graph. And it's going to commit to that permuted adjacency matrix. The verifier is then going to send a random bit. And now there are two possibilities. So if the bit is 0, then what the prover will do is open all the commitments and also reveal the permutation pi. And jumping ahead here, the verifier in that case is just going to check that all the commitments were opened correctly and that the committed graph indeed corresponds to that permutation of the initial graph G. Okay, so graph isomorphism is also a hard problem. So that's why the prover has to reveal to the verifier the permutation that it used. And that allows the verifier to just go one by one and check that indeed what was opened is a permuted copy of the original graph. And on the other hand, if B is equal to 1, then what the prover does is only open the entries in the adjacency matrix that correspond to the permuted cycle in the graph. And the verifier then checks that everything was opened properly, all the commitments were opened correctly, and that what was opened is indeed a cycle. It's easy to check a cycle if I only open n edges and I just walk, check that everything goes around and ends up back where it started. Okay, so is the protocol clear before we go into some analysis of it?
Just the notation, what is this little c?
That's the cycle.
Cycle.
Yeah, so this pi c is a little bit of overload notation because you're now also permuting edges, not just vertices, but yeah.
Sorry, can I ask something?
Oh, yeah.
Please comment a bit again about the isomorphism. So what is the intuitive mechanics behind us permuting the graph?
You mean why do we do it or how do we do it?
Yeah, like no, why do we do that? So like, can we
We'll
always
see maybe in the analysis. Maybe in the analysis we'll see why we do it. Yeah, but you can ask me again if it's not clear afterward. So let's see. Here's just an example. I wanted to do a 4x4 example, but it ran out of space on the slide even. Oh, question?
There is someone raising their hand.
Okay. Yeah. So yeah, please.
Ahmed?
Hello, can you hear me? Can you hear me?
Oh, we can't hear.
He's speaking, but yeah.
Maybe I don't know if anyone's monitoring the chat.
Can you hear me?
Oh, yes.
I just want to ask about in fact, here the classical proof not needs to be interactive. Now we had zero knowledge at the expense of interactivity here, right?
And now here this is interactive. Yes, it's a 3-round protocol.
In general, we can add zero knowledge properties without no extra cost. But
so you're asking about whether we can have non-interactive zero knowledge?
Almost. I'm asking about here the classical proof is in the NP style. We just show the Hamiltonian cycle. But when we need zero knowledge property, here we add extra cost. So
yes.
In this example, the zero knowledge property comes with extra cost, right?
Yeah, in this example, it's going to be more expensive than just having the verifier check the cycle on its own, for sure. But we're getting more properties out of it, right? It's more expensive, but we're getting more out of it.
Yeah. In this example, is there a way without extra cost having zero knowledge?
Yeah, so when we get to talking about snarks, which I'm sure many people are going to focus on how efficient you can make the verifier, and in that context, you can basically you can get you don't have to pay the price of blowing up the complexity of the protocol for the verifier in that case. Yeah, so that'll be, I don't think it's going to be covered today, but I'm sure later in the week it'll be covered.
Thanks.
Good. So let's just give a quick example. So what's going on here is that we have this graph G. The prover, I'm doing this kind of from the viewpoint of the verifier now. So the prover has permuted the vertices of the graph, which ends up permuting the associated adjacency matrix. It sends over commitments entry-wise to the elements of the matrix. The verifier then sends a random challenge. When the challenge is 0, the prover opens the entire adjacency matrix along with the permutation. So in this case, the permutation I applied was just mapping the vertex labeled 1, mapping that to 3, mapping 3 to 2, and mapping 2 back to 1. And you can check that this adjacency matrix is what you get if you apply that permutation to that graph up there. And then the verifier can check that everything was done correctly. Whereas if the challenge was a 1, then what the prover is going to do is going to only open the entries in the matrix that correspond to the cycle. So here we have a cycle because we have an edge from 1. This is indicating an edge from vertex 1 to vertex 3. There's an edge from vertex 3 to vertex 2, and then there's an edge from vertex 2 back to vertex 1.
And that was in the computer graph.
What's that? That's in the permuted graph. Yeah, because the prover committed up here. So once it commits, it can't undo it. So this is going to be in the permuted graph, right? Which is why it doesn't. Oh, I guess I picked a bad example. Yeah, there's only so many permutations when you have 3 vertices. So yeah, I guess it's funny that it worked out. I didn't plan for it to come out that way. But yeah, it'll be in the graph that the prover committed. So it's really, and this is a good way to think about it. It's really in this graph here but the prover is only opening these entries. So this is different from that, but only opening those 3 entries. Good. So let's see. I forget the order I wanted to say this, but let's just think about soundness, right? So think about whether the prover will be able to convince the verifier that a graph is Hamiltonian when it's not Hamiltonian, whether the prover can convince the verifier with probability any better than 1/2, right? There's only 2 possible challenges here, so there's only 3 possibilities. Either the prover never convinces the verifier, it convinces it for 1 possible challenge, or for both possible challenges. So doing better than 1/2 means that it's succeeding on both possible challenges. So what does it mean if the prover can succeed on both possible challenges? Well, it means that the prover sent some commitment to an adjacency matrix in the first round, and then it's able somehow to answer correctly both to a 0 challenge and a 1 challenge. Well, if it opens correctly to a 1 challenge, that means that there is a cycle in this committed graph. If it opens correctly to a 0 challenge, it means that the adjacency matrix that it reveals, number 1, has the same cycle in it. And why does it have the same cycle? Because the properties of the commitment scheme means that the prover cannot open things in 2 different ways. It already showed us, or it has the ability to give us a cycle when we send it a 1. So that cycle is still present in the when we open up the entire adjacency matrix. And number 2, that adjacency matrix is isomorphic to the original graph G. And so that means that we can map that cycle, right, under the inverse of the permutation back to the original graph and obtain a cycle in the original graph. But that contradicts our starting point that there was no cycle in the graph, right? We started by asking the prover to convince the verifier on both challenges, even when there was no cycle. Because what we see is that it's not possible, right? If there's no cycle in the graph, then no prover, assuming this is a statistically binding commitment scheme, or perfectly binding, no prover is going to be able to convince the verifier with probability any better than 1/2 in this 3-round protocol. Is that clear? I mean, this is like, I think this is the first example we're seeing of kind of a non-trivial interactive protocol or interactive proof. And so I kind of just want to make sure everyone agrees that this 3-round, module here gives us soundness 1/2 and perfect completeness.
In the second case, I'm just checking that it is a cycle. I cannot.
Yeah, you can't relate it to the original graph. So actually, that's a great point. Is that you can cheat with probability 1/2.
How do I relate this cycle to the initial?
You don't, and you better not be able to, because I want to prove this is 0 knowledge.
But then I could just am I committing to a cycle here somehow in the beginning, or am I just
whose I is that? Are you the prover or are you somebody else? Well, the prover is committing to the graph, to a permuted copy of the graph.
But what prevents me from opening just any cycle that is not related to showing any cycle that is not related to the committed adjacent?
Yeah, what prevents you is that if you committed to the original graph in the first round, then that's what prevents you here. Then if there's no cycle in that original graph, you're going to be stuck over here, right? So if G,
how can you test if this? So am I committing to the entries like 1 by 1?
Yeah,
like you can open entries 1. Oh,
yeah, 1 by 1, 1 by 1. Yeah. That's why I didn't, you could commit to the entire matrix with a big box here, but no, I want to commit to them entry-wise, and then I can choose which ones I open and which ones I don't. Good. So everyone agrees that this gives you soundness 1/2. So I mean, I should say it as a question, not as a statement. But does everyone agree? Okay. Good. So soundness 1/2 is not good enough, but what we can do now is we can amplify, or we can reduce the soundness error as much as we like by repeating the protocol multiple times. And in particular, if we want soundness error 2 to the minus lambda, then we can just take that 3-round protocol and sequentially repeat it lambda times. So each time, and then the verifier accepts only if all those lambda interactions were all accepting. So we still have perfect completeness. As far as the soundness, right, each time the prover can potentially try to cheat in the subprotocol with probability at most 1/2. But that means that the probability it can successfully cheat all those lambda times is going to be at most 2 to the minus lambda. Yeah, and if you're bored, you can think about what happens if you do it in parallel. Good, and the theorem is that if the commitment scheme is statistically binding and computationally hiding, then this is, so I haven't proven this theorem yet, but I want to prove that it's a 0 knowledge proof of knowledge for graph Hamiltonicity. So always showed so far with soundness. I need to show now zero knowledge and proof of knowledge. Actually, people maybe could use coffee now, but let's go forward anyway. So good. So the key property of the 3-round subroutine, I want to show the proof of knowledge property first, right? The key property of the 3-round subroutine, and we already talked a little bit about this already, is that given an initial message from the prover and correct responses to both challenges, we can efficiently compute a cycle in G, right? This is how I argued soundness earlier. I said if the prover could answer correctly to both possible challenges, then there must be a cycle in G. But not only there must be, but we can actually efficiently compute it if we had a way to get it to answer correctly to both possible challenges. And so we can define our extractor based on that observation, right? So what the extractor is going to do, and this comes back to the point earlier we mentioned about having the extractor run the prover multiple times and see what happens when it does so. And this is now the extractor running on the lambda fold sequential repetition of that 3-round protocol, right? That's the theorem was about that lambda round protocol. Lambda iteration protocol. So what the extractor is going to do is it's going to pick some uniform sequence of bits, B1 through B lambda. B1 through B lambda are going to be the challenges that it's going to use when it runs the honest verifier, essentially, with the possibly cheating prover P star. And what it's going to do, it's going to run P star with those challenges, right? B1 through B lambda, just run the honest verification protocol, no problem. It's going to get some transcript V. Okay. Now, at the end of this interaction, right, there are two possibilities. Either the entire transcript was accepting or it was rejecting. If it was rejecting, right, meaning that at some point the prover failed to respond correctly, then this extractor is done. Because what is it going to do? It's going to output the transcript V, and it doesn't have to output any witness in that case, right? It can just output but, because there's no requirement on what it does in the case when it outputs a non-accepting transcript. Otherwise, V is an accepting transcript, right? And when V is an accepting transcript, we then want the extractor to be able to extract a witness to extract a Hamiltonian cycle in the original graph. So what's the extractor going to do? Well, for I equals 1 to lambda, it's going to basically run the prover P star from the beginning again, changing only the ith bit, the ith challenge bit that the verifier sends. Okay, so it's going to keep the initial prefix the same and then send and just flip the ith bit. Okay, so it does this basically for all possible, for all I. And if ever P star responds correctly to that flipped bit, right, we know already it responded correctly to BI because we have an accepting transcript. If it also responds correctly to the complement, then we have, right, in that ith round, in that ith iteration, we have an initial commitment, and we've been able to obtain successful responses to both possible challenges. And that means we can compute the cycle in the original graph G the way we discussed earlier. And so in that case, the extractor has found a witness, and it can output the original transcript V, okay, along with the witness C. And the only other possibility is that after all these lambda iterations, the extractor was never able to get another response from the prover, in which case it just outputs fail. So why does this work? So first of all, it's really immediate that the V that the extractor outputs is identically distributed to an interaction of P star with the honest verifier, right? So that's just because of the way I defined it, right? The transcript V is defined in the first line, and it's just the interaction of P star with an honest verifier using random challenge bits. So what we need to show is that with high probability, whenever V is an accepting transcript, the extractor will succeed in outputting a witness. Whoops. So let's think about it. So now there's not just a single challenge, there are lambda challenges. And so there are more possibilities of what the prover might do. But there are really only 3 interesting cases. So one case is where the prover responds correctly to no sequence of challenges, meaning that the prover successfully convinces the verifier with probability 0. It's kind of a trivial case, then the extractor doesn't really have to do much. I mean, the extractor will still work, but it never really has to output a witness, so no problem. The second case of interest is, let's say P star only responds correctly to exactly one sequence of challenges. Okay, there's only one lambda bit string of challenges on which the prover will always respond correctly. Well, in that case, the probability that V is an accepting transcript is at most 2 to the minus lambda. It's already negligible. And so the extractor will actually fail in that case, but it's okay because in any case, the prover is only convincing the verifier with negligible probability. Okay, and remember the requirement was that that the probability that we get that the extractor outputs an accepting transcript without a witness is negligible. Here, the probability that it outputs an accepting transcript at all is already negligible. So the only other case to consider is if P responds correctly to 2 or more sequences, right? So it could be that the prover does a really bad job and it answers correctly only with probability 2 times 2 to the minus lambda. But even in that case, the extractor will be able to compute a correct witness whenever V is accepting. It'll still happen with only negligible probability, but still whenever V is accepting, E will succeed in outputting a witness. So the way that to think about it really is via a graph, right? Think about it as a walk down a binary tree, right? So each branching point here corresponds to one of the 2 possible challenges from the verifier. Here we have 3 iterations, so lambda is like equal to 3. And let's say we have like the extractor's initial walk down this binary tree, had it choosing the 0 challenge, the 1 challenge, and the 0 challenge, and then ending up in this accepting configuration here. I don't know why the heart is green, but anyway, so this accepting configuration here, that's where the extractor found itself at the end of the first step of its execution. And we said before that we're looking at the case now where the prover convinces the verifier at least on at least 2 different sequences of challenges, right? Which means that there's another leaf of this tree for which the prover would convince the verifier. We don't know a priori where in the tree that will be, but we know that there's at least one more leaf of the tree where if we went down to that leaf, we would also get an accepting transcript. Okay, and if and we want to try to find it. Now, it seems like we might be a little bit stuck because how are we going to search over this exponentially large tree? But in fact, it suffices to look at the neighbors of each vertex on this path. So it suffices not to look at all 2 to the lambda leaves, but only to go one off the path to the right, and then down here on the second level to the left, and then down here on the third level to the right. And that will guarantee that you find a second accepting transcript. So why is that the case? So let's just imagine, right, that the second accepting transcript happens to be here. There may be others, by the way, but let's say there's at least one here. Well, what does that mean? That means that if we followed this path all the way down here, we would get a sequence of accepting interactions with the prover. And that means in particular that when we just go one further, that we get a second accepting subprotocol in the second iteration. We don't have to actually follow down the third. We don't really care. What we have is a situation here where in the second iteration, we initially got one accepting transcript with challenge 1. And then when we hit the second iteration and flip the bit, we get a second iteration with the same initial message. And from that, we can extract a witness. So questions on that? So we get an efficient extractor then, right? We get one that operates in like order of lambda time.
It's somehow necessary that the permutation used by the prover is the same in all.
No. So it doesn't rely on that, right? And it shouldn't be, because an honest prover would not use the same permutation every time either. So what it relies on is that in the first iteration, the prover can use whatever permutation it wants. In the second iteration, it can use whatever permutation it wants. But in this second iteration, we found an initial message from the prover such that the prover in that iteration could respond correctly to both the 0 and the 1 challenge. And whatever permutation it happened to use there, we were able then to extract that. Then
I know the cycle.
The extractor knows the cycle, yeah.
The extractor knows the cycle for
it learns it.
permutations and the adjacency matrix.
Oh,
you cannot map.
No, he can, right? Because the extractor has now from the 0 challenge, it has some permuted adjacency matrix of the original graph, and it knows the permutation. And from the 1 answer, it knows the cycle in that permuted graph.
Yeah, this is a different.
No, it's the same, right? Because so I don't have a lot of board space, but like, imagine, so here's iteration 1. Whoops, and here's iteration 2. Look, I have an efficiency improvement. I can collapse the REMs. Okay. So I think people can see this. So the point is that here, I don't even care what he did, but he did make me accept fine. Here, he sent me some committed adjacency matrix. And I sent a 0, let's say, in the first time, and I got back the open matrix plus the permutation pi. Then I did this walk down the tree, and I ran the first iteration using the same challenge here.
You're expecting that the prover is behaving similarly as in the first iteration.
Okay.
He's using the same randomness.
Yes, so I control the prover, so I'm going to fix his randomness actually. Yes, yeah. So I maybe should have been more clear on that point. I mean, in fact, P star might be all powerful and not be randomized at all. But if it's randomized, then the first thing you would do is pick a random string and fix the string to that value and fix it from then on. Yeah, no, that's a good point. I should have made that clear. I was thinking of an all powerful prover. It doesn't even have to be randomized.
So earlier we used the definition that the verify can simulate the entire interaction with the prover with itself, and that's how we know.
Well, this is the proof of knowledge property. This is not the zero knowledge property. So the proof of knowledge property, we care about protecting the verifier against a malicious prover.
Okay. So
by the way, I don't want to like hold people back if they want coffee. So, you know, I'm gonna keep talking, but like if you're bored, but if you're not bored, but if you just really need coffee or need a bathroom break or like need to stretch your mind or something, I won't even look. Zero knowledge who leaves, but
just one comment to give intuition why this doesn't break the zero knowledge. Basically, the power we give to the extractor is that it knows this pi star, this p star, so it knows what true on us, but the verifier does not know what p star is. So yeah, I don't know.
yeah, that's part of it. I mean, it holds even if like the prover is an honest prover. So even if the verifier does know P, it's still zero knowledge, but.
I'm confused with what's the reasoning behind that we're able to control what the P star.
Yeah, so the way, I mean, it's a little bit because of the way that I set up the definitions, right? So the definition said that for all P star, there exists an extractor, right? So that means that if there exists, you know, Python code for P star, then there exists Python code for the extractor. But in particular, the extractor can embed the Python code of the prover inside of it. I didn't say that that's allowed or not allowed. And so, or maybe a better way to think about it is that the Python code for the extractor can call the Python code for the prover as a subroutine if it likes. And so, you know, it's allowed. Or if you like, you know, the Turing machines instead of Python code.
This prover is rewindable prover.
Yeah, so, you know, you can think about it. I mean, often people talk about it like rewinding. And that's another way to think about it, is that what you did was you ran the prover to here, then you ran the prover to here, and then you rewound and sent it a different challenge over here. It's equivalent to running it from scratch with the same inputs as long as you fix the randomness. So you can view it either way.
the notion of rewinding implies a notion of fixing the randomness, and
Yeah, if it's a randomized prover, then it implies fixing the randomness, yeah. Okay. Okay, let's look at zero knowledge. And are we starting again at 12 or we have a break then?
We have a break for 15 minutes right now.
Is there another talk at 12 or is there something? Okay, I think I'll definitely finish this by 12, but it won't give people a lot of time for coffee, but.